They told you the solar system gets quieter the farther out you go. Closer to the sun means heat, means chaos, means storms. Farther out means cold, and stillness, and silence. That picture is intuitive. It is logical. It is completely wrong. Neptune, the eighth planet, the most distant of the major worlds, the one that receives sunlight 900 times weaker than Earth's, is the most violent planetary atmosphere in the entire solar system. Its winds move faster than the speed of sound. Its storms are wider than the Atlantic Ocean and reverse direction without warning. Everything you assumed about the cold outer edge of the planets is about to collapse. The farthest giant is also the most furious, and nobody fully knows why. A small team poured real time into making this as accurate and engaging as possible. If it landed for you, a subscribe is the best way to say so. In 3, 2, 1, liftoff. Picture the solar system the way almost every human being does when they first encounter it, as a gradient. Hot and violent at the center, cooling and calming as you move outward. The sun sits at the middle of everything, a nuclear furnace 400,000 times more massive than Earth, radiating energy in every direction at a rate so enormous that no unit of measurement built for human experience can hold it. Close to the sun, that energy matters. Mercury, the innermost planet, has no atmosphere capable of moderating what the sun does to its solar radiation, strips away any gas that tries to collect, and the surface temperature swings between 430 degrees Celsius on the day side and negative 180 degrees on the night side within a single planetary rotation. Venus, the next outward, is a catastrophe of a different kind. A runaway greenhouse nightmare where the atmosphere itself became the enemy, trapping solar heat until the surface reached 465 degrees Celsius, hot enough to melt lead, sustained, permanent, with a pressure at the surface that would crush a submarine. Earth follows temperate, alive, balanced by its oceans and its magnetic field, and its just right distance from the source. Mars stands farther out, colder and thinner, still scarred by ancient floods and volcanic activity, but now largely a frozen desert swept by dust storms that occasionally swallow the entire planet. Then the asteroid belt, and then the threshold between the inner and outer solar system. Past that threshold, the picture changes. Jupiter looms the largest planet, a world 11 times Earth's diameter, with storms embedded in its cloud bands that have been continuous since before the telescope was invented. The Great Red Spot, Jupiter's most famous feature, is a high-pressure storm system wider than Earth that has been spinning for at least 3 centuries and possibly much longer. Jupiter is violent and active and enormous, and it sits close enough to the inner solar system that its gravitational influence shapes asteroid trajectories and protects the inner planets from some of the bombardment they would otherwise receive. Then Saturn, ringed and stately but still dynamic, its own storm systems, its hexagonal polar vortex, its banded atmosphere driven by winds that reach several hundred kilometers per hour. But already, even at Saturn, the sense of the gradient is asserting itself. Saturn is dimmer and colder than Jupiter. Its light, by the time it reaches Saturn, is weaker. Its atmosphere is less energetic, its features less dramatic. The gradient is working. Then Uranus, and the shift becomes more pronounced. Uranus sits at approximately 19 times Earth's distance. The light reaching Uranus is 360 times weaker than what falls on Earth. It is cold, negative 214 degrees Celsius at the cloud tops, and when Voyager 2 flew past it in January of 1986, the images it returned showed something that surprised the mission team. Almost nothing. A nearly featureless blue-green sphere, smooth and still, with minimal visible cloud structure and nothing approaching the dramatic storm bands and massive vortices that characterize Jupiter or Saturn. Uranus, the seventh planet, looked exactly like a world that had run out of atmospheric energy. It looked like the gradient was finishing its work. And then, at the very end, Neptune, the eighth planet, the farthest major world in the solar system, sitting at approximately 30 times Earth's distance from the Sun, another 10 astronomical units beyond Uranus, another enormous step outward into the cold and the dark. The sunlight reaching Neptune is 900 times weaker than what reaches Earth. Not dimmer in the way that a cloudy day is dimmer, not reduced in the way that shade is reduced. 900 times. A mathematical gulf so large that the Sun itself, viewed from Neptune's cloud tops, is no longer a disk of light, but a brilliant point, the brightest object in the sky by a vast margin, but a point, a star, a source of illumination so faint that noon on Neptune, in terms of the raw solar energy input into the atmosphere, is the rough equivalent of a dim and overcast twilight here. The Sun is present above Neptune. It is not warm. It is not a driver. It is an ambient glow against the darkness of the outer solar system, and Neptune is cold. The temperature at its cloud tops sits at approximately -218 degrees Celsius, -360 degrees Fahrenheit, which is 55 degrees above absolute zero, the theoretical floor below which temperature cannot descend because molecular motion itself would cease. At -218 degrees, no water exists in any liquid state. No chemistry operates at anything resembling biological speeds. The thermal energy available to individual molecules is so minimal that what passes for atmospheric gas at those altitudes behaves in ways that have no terrestrial equivalent. The cold is not a detail. The cold is structural. It defines what Neptune is allowed to be, physically, if you build your expectations from the solar energy budget alone. And here is the intuition that this entire story is built to dismantle. Those facts: the distance, the weak sunlight, the profound cold, the logical extension of the gradient that smoothed Uranus into apparent featurelessness, all conspire to suggest, strongly and reasonably, that Neptune should be the quietest major planet in the solar system. The end point of the gradient, the place where the solar system exhales and goes still. The most remote major world should be the most dormant, the most stable, the most meteorologically inert. Everything points that way. The physics of solar energy input says so. The precedent of Uranus says so. The entire logical architecture of the distance equals quiet model says so. Neptune is also beautiful, and beauty reinforces the assumption in ways that are harder to account for, but entirely real. When Voyager 2 arrived at Neptune in August of 1989 and returned the first close-range images of the planet, what those images showed was a deep and vivid blue, not the muted blue-green of Uranus, but something richer, more saturated, the kind of blue that reads as oceanic depth and translucent atmosphere and quiet vastness. The color comes from methane in Neptune's upper atmosphere. Methane absorbs the red wavelengths of sunlight and reflects the blue. The result, under the particular illumination and camera geometry of Voyager 2's approach, was a planet that appeared luminous, serene. The color of a gemstone or a clear sky, concentrated and held steady at the edge of the solar system in the dark. Everything about the visual impression Neptune creates, the blue, the distance, the cold implied by that distance, the quiet Uranian precedent, suggests a world that has settled into a kind of frozen atmospheric peace. A world that time and distance and cold have stilled. It is exactly wrong. Neptune was discovered through mathematics, but what its distance and temperature seemed to promise, that atmospheric quietness the gradient demanded, was a prediction the planet has been refuting for as long as humans have had instruments sensitive enough to look at it carefully. The refutation did not come all at once. It came in layers, each instrument revealing a new dimension of Neptune's violence that the prior instrument had missed. Each layer of evidence requiring a further revision of the intuitive model, until the intuitive model itself became the story of a failure, the story of an assumption that was built from accurate facts and arrived at a completely wrong conclusion. To understand why the assumption was wrong requires understanding what the assumption left out. The solar energy budget, the calculation of how much energy the Sun delivers per square meter at Neptune's distance, is a real and accurate physical quantity. The inverse square law is not in dispute. Neptune really does receive approximately 1/900th of the solar energy that reaches Earth. But the solar energy budget is only one term in the equation that governs planetary atmospheric behavior. It is the external term, the energy input from the star. There is a second term, the internal term, that describes the energy a planet generates from within and delivers upward into its own atmosphere. For the rocky inner planets Earth, Mars, Venus, Mercury, the internal heat term is real but small compared to the solar input. It shows up primarily as geothermal energy and volcanic activity, not as a dominant driver of atmospheric dynamics. For the giant planets, the internal term becomes much more significant. Jupiter, Saturn, and Neptune all emit more energy into space than they receive from the Sun. The assumption that drove the gradient intuition treated the internal term as negligible at Neptune, as though the planet, being cold and far away, must have exhausted its interior energy long ago. That assumption was wrong. Neptune's interior has not gone cold. Its internal heat output, per unit of solar energy received, is the largest of any giant planet, and the atmosphere is the consequence. There is one more element of Neptune's character that the gradient intuition failed to incorporate, and it is the one that makes Neptune's violence feel, when the evidence is fully assembled, most personally surprising. Neptune is not a new world. It is not recently discovered in any sense that should produce unexpected behavior. It formed at the same time as the rest of the solar system, approximately 4.5 billion years ago, from the same reservoir of material that became Jupiter and Saturn and the rocky inner planets. It has been there, orbiting the Sun, for 4.5 billion years. It has not changed in any dramatic way over the timescale of human history. Its winds were moving at these velocities before humans existed. Its dark spots were forming and dissolving and forming again before the first animal walked on land on Earth. Everything about Neptune that makes it the most violent major planet in the solar system has been happening for geological timescales, steadily, without interruption, at the edge of the planetary system, while the entire history of life on Earth played out and concluded and evolved into the creatures now describing it. Neptune has been doing this all along. The surprise is ours, not the planet's. It is the surprise of a species that looked at a beautiful blue point of light at the edge of the solar system and assumed, without asking, that such a remote and cold and dimly lit thing must be quiet and only discovered when it finally sent a spacecraft there after 12 years of travel, and only confirmed more completely in every subsequent decade of observation that the assumption had been wrong from the beginning. Neptune was discovered through mathematics, before it was ever seen by an eye or a telescope pointed at the right piece of sky. In the 1830s and 1840s, astronomers tracking Uranus through its orbit noticed that the planet was not quite following the path that Newtonian mechanics predicted it should follow. Something was gravitationally tugging it off course, something massive enough to perturb a planet's orbit, something that had to exist at a certain location for the perturbation pattern to make sense. Two mathematicians, the Frenchman Urbain Le Verrier and the Englishman John Couch Adams, calculated independently where that something would have to be. In September of 1846, the German astronomer Johann Galle pointed a telescope at the coordinates Le Verrier had specified and found Neptune within 1 degree of the prediction. A planet found by calculation before it was observed. A triumph of theoretical physics. But Neptune has humbled theoretical expectations ever since. Because the more carefully scientists have looked at it, first with Voyager 2's instruments during the few days of closest approach in August of 1989, then with Hubble's systematic monitoring program that began in the 1990s, then with ground-based instruments including the European Southern Observatory's Very Large Telescope, and most recently with the James Webb Space Telescope, the more Neptune has refused to be what the gradient said it should be. Every instrument pointed at Neptune has returned data that required a revision of prior assumptions. Every observation has added a new piece of evidence that the comfortable model of the outer solar system, with its well-behaved gradient from hot and violent to cold and quiet, had missed something fundamental about what was happening at the edge of the planetary family. The discovery that began the revision and that still anchors everything that follows is this: Neptune is the windiest world in the solar system, not among the windiest, not faster than expected for a cold outer planet, which would already be remarkable. The absolute record holder across all major planets, measured against any comparable atmospheric system anywhere in the solar system. At Neptune's cloud tops, wind speeds reach approximately 2,400 kilometers per hour, approximately 1,500 miles per hour. The speed of sound at sea level on Earth, in air at standard temperature and pressure, is approximately 1,224 kilometers per hour. Neptune's measured wind speeds exceed the speed of sound by an amount that is not marginal. They are supersonic in the most direct physical sense, and they are sustained, not transient. They are not the product of a local explosive event or a singular storm. They represent the background state of Neptune's upper atmosphere. The fastest winds ever measured in any planetary atmosphere in the solar system belong to the coldest, most distant, most dimly lit major planet in that solar system. That fact sits at the center of everything this story is about. The rest is explanation: the storms, the internal heat, the decades of observation that have documented what Neptune is actually doing behind that beautiful, serene, deceptive blue. But the fact itself is where the comfortable lie first cracks open. The gradient was supposed to lead to stillness. It led, instead, to the most violent atmospheric winds we have ever recorded. Neptune is a giant planet, specifically an ice giant, a subcategory distinct from the gas giants, Jupiter and Saturn, in ways that matter for the story we are telling. Jupiter and Saturn are composed primarily of hydrogen and helium throughout their enormous volumes, with no meaningful internal reservoir of what chemists would call icy materials, water, ammonia, methane, because their tremendous gravitational compression keeps their interiors at temperatures where those molecules exist in exotic, metallic, or plasma states, rather than anything resembling ice. Neptune and its structural twin Uranus are fundamentally different in composition. Their interiors are dominated by what planetary scientists call ices, water, ammonia, and methane under enormous pressure, states of matter that are neither the familiar solids nor the familiar liquids of everyday experience, but high-pressure, high-temperature phases with unusual physical properties. Above those icy interiors sit gaseous envelopes of hydrogen and helium, with methane mixed in at the outer layers, the methane that gives Neptune its color, and the same methane that will become crucial to explaining Neptune's violence in a way nobody fully predicted. Neptune's diameter is approximately 49,500 kilometers, roughly 4 times the diameter of Earth, but dramatically smaller than Jupiter's approximately 142,000 kilometers, or even Saturn's approximately 120,000. At this size, Neptune falls squarely in the ice giant class, large enough to have captured a substantial hydrogen-helium gaseous envelope during formation, but not so massive that it became the hydrogen-dominated colossus that Jupiter represents. Neptune's mass is approximately 17 times Earth's mass. Its rotation period is approximately 16 hours and 6 minutes faster than Earth, meaningfully affecting how the Coriolis force organizes atmospheric motion into jet streams and circulation patterns. And it has 14 known moons, the largest of which, Triton, is one of the most scientifically interesting objects in the outer solar system. A retrograde orbiting captured Kuiper belt object with active nitrogen geysers and a surface covered in exotic ices. But Triton is not the story here. The story is the planet itself, its atmosphere, its winds, its storms, and the engine hidden beneath the blue that makes it the most violent major world in the planetary system. Neptune's position in our cultural picture of the solar system compounds the intuitive error in a way that matters for understanding how striking the evidence against it is. Neptune is not a planet that comes up often in casual scientific conversation. When people think of the outer solar system, they tend to stop at Saturn, at the rings, which are iconic and immediately recognizable, and which have anchored public understanding of the outer solar system, since Galileo first noticed that Saturn had extensions he could not explain. Beyond Saturn, the outer planets exist as increasingly abstract entries in a list. Uranus, the tilted ice giant; Neptune, the farthest one; Pluto, which was reclassified. Neptune occupies a specific cultural position as the place where engagement with the solar system tends to trail off. It is the last real planet. It is the exit. In that cultural position, Neptune is granted a kind of atmospheric amnesty. It is allowed to be whatever distant, cold, unexamined things are assumed to be, which is to say, it is allowed to be still. The science has never supported that assumption, but the assumption has been durable precisely because Neptune is so difficult to study. Only one spacecraft has ever visited Neptune directly: Voyager 2's flyby, in August of 1989, was not a brief stop, but a genuine observational event. The spacecraft carried instruments designed specifically to characterize Neptune's atmosphere, magnetic field, and moon system, but it was still a flyby, measured in days. The highest resolution close approach phase lasted hours. In those hours, Voyager 2 returned more information about Neptune than all previous observation combined. It also raised more questions than it answered, which is the most honest summary of what happens when human instruments get close to a world that has never been examined carefully. Every answer opened 3 new questions. Every measurement revised the model, and then Voyager 2 passed through and continued outward into interstellar space, and Neptune was left behind again, still raging, still cold, still beautiful, still roughly 30 times farther from the Sun than Earth, and still, for the next 3.5 decades, only observable in the limited sense of what ground-based and Earth orbit telescopes can achieve across approximately 4 to 5 billion kilometers of intervening space. Understanding what Neptune is requires also understanding where it sits in the taxonomy of planetary objects. The solar system has 2 broad classes of giant planet, gas giants and ice giants, and Neptune's membership in the ice giant class defines something important about its internal composition that becomes central to part 3 of this story. Jupiter and Saturn are gas giants, dominated throughout their enormous volumes by hydrogen and helium. Their tremendous gravitational fields compress these light elements into exotic states at depth. Metallic hydrogen in Jupiter's interior, where the pressure is so extreme that hydrogen conducts electricity like a metal, but the bulk composition remains the lightest elements in the periodic table. Ice giants like Neptune and Uranus have a fundamentally different interior structure. Beneath their hydrogen-helium gaseous envelopes, their interiors are dominated by what planetary scientists call ices, water, ammonia, and methane under enormous pressure. These are not ice in the everyday sense. At the pressures and temperatures present deep inside Neptune, reaching potentially thousands of degrees and millions of atmospheres of pressure, water, and ammonia and methane exist in strange high-pressure phases, possibly including what some theoretical models describe as superionic water, where oxygen atoms lock into a crystalline lattice while hydrogen ions move through it as a conducting fluid. The properties of these deep interior materials are not fully characterized because we have never sampled them directly, but their existence, their composition, and the physical state they occupy has consequences for how heat moves through Neptune's interior that are directly relevant to why the planet's surface atmosphere is so violent. The methane in Neptune's upper atmosphere that gives the planet its color is the same compound that appears in vastly higher pressure form in the interior. At cloud-top altitudes, where the pressure is approximately 1 bar, methane is a gas mixed at a few % concentration into the hydrogen-helium envelope. It absorbs red light and reflects blue. That much is well understood and accounts for the beautiful color that makes Neptune visually arresting. But methane is also a greenhouse gas, a molecule that, when present in an atmosphere, absorbs infrared radiation that the surface or deeper atmospheric layers are emitting and prevents that radiation from escaping freely into space. On Earth, methane is one of the most powerful greenhouse gases, more effective at trapping infrared radiation per molecule than carbon dioxide. At Neptune, the methane concentration in the outer atmosphere is sufficient to act as a thermal insulator of exactly the kind that becomes crucial to understanding why Neptune still has an active internal heat source, while its structural twin, Uranus, apparently does not. But that argument belongs to part 3, where the energy budget becomes the central question. For now, it is enough to note that the same molecule responsible for Neptune's calming blue exterior is also, potentially, one of the reasons its interior remains violent, a chemical character that simultaneously produces the planet's most visually serene feature and, as a leading hypothesis, contributes to its most physically aggressive behavior. What makes Neptune's wind record especially difficult to reconcile with the gradient intuition is not just the speed, but the context. Neptune receives approximately 1.5 watts of solar energy per square meter at its cloud tops. Earth receives approximately 1,368 watts per square meter. Divide Neptune's wind speed record by its solar energy input and compare that ratio to any other planet, and you find something that should strike anyone thinking carefully about atmospheric physics as extraordinary. Neptune generates more wind velocity per unit of available solar energy than any other body in the solar system, by a margin that cannot be explained by solar energy at all. The sun is not powering those winds. Something else entirely is responsible, and the chase for that something else is the next layer of this story. But first, Neptune's violence needs to be fully established, not just its speed record, but its storms, its recurring atmospheric upheavals, the documented history of a planet whose atmosphere has been doing something that no outer giant was supposed to be able to sustain. The beauty of Neptune at the moment of first encounter, the blue, the apparent calm, is real, and it is still sitting in this story like an unresolved tension, because the winds are happening behind that beauty, not instead of it. Both things are simultaneously true about Neptune. It is one of the most visually arresting objects in the solar system, and it is one of the most physically violent. The distance does not mute the violence. The cold does not suppress it. The faint sunlight does not starve it. Neptune's atmosphere is raging, and has been raging, on a scale and at a velocity that the assumptions of outer solar system planetary science systematically failed to predict. That failure begins with the wind record, and what it points toward, the storms, is where the failure gets specific and documented and unmistakable. There is a physical consequence to wind moving faster than sound that is worth holding on to before we go any further. On Earth, when a storm is approaching, you receive information about it. Before it arrives, you can hear it building, you can feel pressure changes, you can detect signals traveling through the medium of the air at the speed of sound ahead of the storm itself. The storm is fast, but the air, as a medium for information propagation, is faster. You have warning. You have the acoustic advance of the event before the event itself reaches you. At Neptune's cloud tops, that relationship inverts. A wind system moving at approximately 2,400 kilometers per hour, supersonic by Earth atmosphere standards, is moving faster than any acoustic information could travel through the gas ahead of it. There is no advance signal. The atmosphere at Neptune is being displaced faster than it can communicate that displacement to adjacent regions via sound. This is not a metaphor. This is a physical description of what Neptune's wind field is doing to the medium it moves through, and it reframes the violence at Neptune from the merely impressive into the categorically different. Wind, at its most fundamental, is atmospheric gas in motion driven by pressure gradients. Pressure gradients arise from temperature differences. Where the atmosphere is warmer, gas is less dense and rises. Where it is cooler, denser gas sinks and flows laterally to replace what rose. The circulation this generates: rising warm air, lateral spreading aloft, sinking cool air, surface level return flows, is the engine of weather on every planet, with a thick atmosphere. The speed of the resulting winds depends on the temperature gradient, the rotation rate of the planet, the scale over which the circulation operates, and the viscosity of the gas itself, how much internal friction the moving gas experiences as it accelerates. On Earth, those four factors combine to produce maximum sustained wind speeds in the strongest tropical cyclones of roughly 250 to 300 kilometers per hour at the surface. On Jupiter, where the planet is much larger, rotates faster, and has a more energetic internal heat source, jet stream velocities reach approximately 500 to 600 kilometers per hour. On Neptune, the combination of an internal heat source we will examine in Part 3, the planet's physical scale, its rapid 16-hour rotation, and atmospheric temperatures so cold that molecular friction is dramatically reduced, pushes wind velocities to approximately 2,400 kilometers per hour. That last factor, the role of extreme cold in reducing atmospheric friction, deserves expansion because it is counterintuitive in a way that the gradient intuition obscures. One might assume that colder, denser, atmospheric gas would be harder to move, would generate more friction, would resist acceleration. In fact, the viscosity of an ideal gas decreases with temperature in a way that allows cold atmospheric gas to accelerate more freely than warm atmospheric gas under the same driving force. The deep cold at Neptune's cloud tops does not resist the winds. In a real physical sense, it enables them. The same cold temperature that the intuition points to as evidence of Neptune's quiescence is actually one of the factors contributing to its wind record. The gradient argument contains within itself, if read carefully enough, a physical mechanism that runs in the opposite direction from the conclusion the argument draws. Neptune's wind system has a structure that makes it stranger still. The retrograde equatorial jet, the band of atmosphere at low latitudes, moving opposite to the planet's rotation at approximately 400 meters per second, or roughly 1,440 kilometers per hour, is the dominant feature of Neptune's large-scale atmospheric circulation. Most giant planets with active atmospheres have equatorial winds that blow in a prograde direction, following the planet's spin. Because the planet's rotation transfers angular momentum into the equatorial atmosphere, and the Coriolis effect organizes that momentum into westward flowing jets at high latitudes and eastward flowing jets near the equator. Jupiter and Saturn both follow this pattern. Neptune inversé. At Neptune's equator, the dominant atmospheric motion is westward retrograde, running counter to the planet's eastward rotation, and the strong prograde jets appear at mid-latitudes, one jet per hemisphere, rather than the complex multi-jet structure seen at Jupiter and Saturn. Recent research published in 2025 from the Weizmann Institute of Science, examining the unified mechanism behind giant planet equatorial jets, has identified that the direction of the equatorial jet prograde on Jupiter and Saturn, retrograde on Uranus and Neptune, is connected to how deeply the jet systems penetrate into the planet's interior and how intrinsic heat fluxes drive convective motions in the upper atmosphere. At Jupiter and Saturn, the jets penetrate deeply, and convective Rossby wave generation near the equator drives angular momentum toward low latitudes, producing the prograde equatorial jet. At Neptune, the shallowness of the jet system confined to the outermost 0.2% of the planet's mass, approximately 1,100 kilometers deep, combined with the specific character of the internal heat flux, produces the retrograde flow at the equator through a different angular momentum transport mechanism. The mathematical details are complex, but the physical implication is important. Neptune's retrograde equatorial jets are connected to the same internal heat source that drives everything else about Neptune's atmospheric violence. The wind direction is not a coincidence or an anomaly. It is a signature of the energy regime operating inside the planet. The shear between Neptune's retrograde equatorial jets and the prograde mid-latitude jets creates zones of intense atmospheric turbulence at the boundaries. Wind shear, the change in wind velocity over a short distance, is one of the primary mechanisms for generating atmospheric instability on any planet with a layered circulation system. On Earth, wind shear at the interface between the troposphere and the stratosphere is responsible for the clear air turbulence that aircraft encounter at altitude. In the developing stages of thunderstorms, wind shear at different altitude levels is a key factor in whether a supercell develops rotation. At Neptune, the wind shear at the boundaries between the retrograde equatorial belt and the prograde mid-latitude jets is not a peripheral feature. It is a major structural element of the atmospheric circulation, generating the instability that cascades into Neptune's most dramatic and most scientifically documented phenomenon, the dark spots. The Great Dark Spot. Any serious account of Neptune's violence has to begin with what Voyager 2 found when it arrived, not because the Great Dark Spot is Neptune's most recent revelation, but because it was the first direct evidence that the gradient had failed, and because what happened to it in the 5 years after Voyager's visit sharpened the failure into something unmistakable. When Voyager 2's cameras began resolving Neptune's disk in the weeks before closest approach, the images showed what initial processing confirmed was an enormous anticyclonic storm system in the planet's southern hemisphere. The storm sat at approximately 20 to 27 degrees south latitude. It measured approximately 13,000 kilometers along its longest axis, making it comparable in scale to the entire diameter of Earth from one side to the other. In Voyager's images, taken through a filter centered at 467 nanometers, it appeared approximately 10% darker in albedo than the surrounding atmosphere, which is why it was called a dark spot rather than a bright one. The darkness told scientists something specific about what the storm was doing. It was a high-pressure anticyclone rotating counterclockwise, and the high pressure at its center was suppressing the upward convection of atmospheric gas that would otherwise carry methane upward to the altitude, where it freezes and forms the bright white cloud deck. By suppressing that convection, the storm was creating a window, a region where the higher altitude methane cloud deck was thinner or absent, allowing deeper, darker atmospheric layers to be seen from above. The storm made itself visible by clearing the clouds that would otherwise hide it. Above and at the margins of the Great Dark Spot, Voyager's cameras documented something that would later become a key piece of evidence about the storm's dynamics: a narrow, bright companion cloud band that the mission scientists nicknamed the Bright Companion. This feature was made of methane ice crystals at high altitude, approximately 50 to 100 kilometers above the altitude of the dark spot itself, and it changed shape and structure continuously throughout Voyager's observation period, forming and reforming on timescales as short as 4 hours, sometimes appearing as a coherent band along the southern rim of the dark spot, sometimes fragmenting into isolated patches, never holding the same configuration between successive Voyager camera passes. The bright companion was the atmospheric equivalent of orographic cloud, like the lenticular cloud that forms over a mountain peak when moisture-laden air is forced upward by the terrain, except what it was being forced over was not a mountain, but a high-pressure atmospheric vortex, pushing gas upward at its periphery until the methane in that gas rose high enough and cooled enough to crystallize and become visible. A third feature, tracked by Voyager during the Neptune flyby, was a smaller, bright cloud structure located between the Great Dark Spot and Dark Spot 2, the second major storm Voyager documented at Neptune, which the mission team nicknamed the Scooter. The Scooter moved eastward at a different velocity than either of the two dark spots, occasionally overtaking them, occasionally lagging behind, and it was caused by something distinct from the anticyclonic vortex structure of the dark spots. It was a convective cloud plume rising from below the main cloud deck, carried eastward by the mid-latitude prograde jets. The Scooter's existence was itself evidence of the atmospheric complexity at Neptune. There were at least 3 qualitatively different classes of atmospheric feature visible simultaneously during the Voyager flyby: major anticyclonic vortices, their high-altitude companion cirrus, and convective plumes driven by deep upwelling. None of these feature types was predicted before Voyager's arrival. All of them appeared in the first days of close-range observation. What Voyager measured of the Great Dark Spot's rotation gives a further sense of its scale and intensity. The storm rotated counterclockwise the anticyclonic direction in Neptune's southern hemisphere with a period of approximately 16 days. The entire vortex, 13,000 kilometers across, completing one full rotation every 16 days. That is a wind speed at the storm's outer margin, where the rotation is fastest, that is consistent with the background atmospheric wind speeds that make Neptune the windiest planet in the solar system. The storm was not just large, it was embedded in and powered by the same supersonic wind field that characterizes the whole upper atmosphere. The scientific community watching the Neptune flyby data arrive was aware that they were looking at something extraordinary. But there was also a framework of expectation operating. The Great Dark Spot looked like a Neptune analog of Jupiter's Great Red Spot, which had been the dominant storm feature of the solar system's largest planet for at least 3 centuries of observation, and almost certainly much longer. If Jupiter's great storm could persist for centuries, a comparable anticyclonic vortex at Neptune, which might have the same basic fluid dynamics governing its stability, should also be long-lived. Scientists expected to return to Neptune's storm with Hubble and find it still there. In June of 1994, Hubble turned toward Neptune with a precision unachievable from the ground and took the first high-quality resolved images of the planet in the 5 years since Voyager's visit. The scientific team prepared to track the Great Dark Spot, to measure how it had evolved, how it had moved, whether it had changed in shape or scale. They had a working scientific model of how the storm should be behaving, built from Voyager's measurements and from fluid dynamics, theory applied to Neptune's atmospheric conditions. That model was about to be invalidated by the complete absence of the storm it described. The Great Dark Spot was not there, not reduced, not relocated to a different latitude, not weakened to the point where it was barely detectable. It was gone, completely, entirely, without observable remnant. Dark Spot 2, the companion vortex that Voyager had tracked in Neptune's southern hemisphere alongside the Great Dark Spot, was also gone. The Scooter, too, had vanished. In the 5 Earth years, less than 4% of a single Neptunian year between Voyager's visit and Hubble's first clear look, every documented storm feature of Neptune's 1989 atmosphere had ceased to exist. And within months of that Hubble observation confirming the storm's disappearance, a new dark spot appeared in Neptune's northern hemisphere, not a surviving remnant, a new formation, different hemisphere, different latitude, different geometry. Neptune had not calmed down in the interval. Neptune had turned over an entire generation of storms. This is the first place where Neptune forces a genuinely new concept onto the story, one that the Jovian analogy actively misled scientists about. Jupiter's great red spot is stable because Jupiter's atmosphere operates in a regime where large anticyclonic high-pressure vortices find stable equilibrium positions within the jet stream structure and can persist for centuries or longer. Neptune's atmosphere operates in a different regime, one where such vortices are metastable at best, with lifetimes measured in Earth years rather than Earth centuries, and where the atmosphere continuously generates new vortices to replace the ones that dissipate. The violence at Neptune is not expressed through the persistence of a single monumental storm, as it is at Jupiter. It is expressed through the continuously regenerating cycle of storm formation, evolution, and dissolution, a meteorological churn that shows no sign of stopping, that has continued across every observation period in which Neptune's atmosphere has been monitored, and that requires a sustained and enormous energy supply to maintain. Since Voyager 2's flyby in August of 1989, 6 dark spots have been confirmed at Neptune in total. 2 by Voyager in 1989, 4 more documented by Hubble in the decades since. The ongoing Outer Planet Atmospheres Legacy Program, a systematic yearly imaging campaign of Neptune using Hubble's Wide Field Camera 3, has been the primary instrument for tracking the dark spot cycle, and the data it has accumulated constitutes the most comprehensive longitudinal record of Neptune's storm activity ever assembled. What that record shows is not a planet that occasionally and unusually generates giant storms. It shows a planet that regularly generates them, with something like a new major dark spot appearing roughly every 4 to 6 years, persisting for 1 to 2 years, and then dissipating. The 2018 dark spot, the most recent major vortex to be documented in detail, and the one that changed what scientists thought they knew about how Neptune's storms behave, was discovered in Hubble images taken in September and November of 2018. It appeared in the northern hemisphere at approximately 23 degrees north latitude and measured approximately 6,000 kilometers across its longest axis, smaller than the 1989 Great Dark Spot, but still of continental scale, roughly the width of the North Atlantic Ocean. Hubble's year-over-year monitoring tracked the storm through its formation and into its subsequent evolution, and the evolution that followed was the part that broke the existing model. By 2019, Hubble's observations showed the 2018 dark spot beginning to drift southward toward the equator, toward the low-latitude wind shear zone, where the retrograde equatorial jets interact with the prograde mid-latitude jets, where prior models predicted that Neptune's dark spots should find their atmospheric death. The established picture of dark spot life cycle, assembled from observations of earlier spots and from fluid dynamics models calibrated to Neptune's atmospheric structure, said that a dark spot drifting equatorward was approaching the region where the wind shear would tear it apart. The storm was heading, in the best available scientific understanding, toward its end. What Hubble found when it imaged Neptune in August of 2020, had no precedent in the 31 years of dark spot observation since Voyager's flyby. The 2018 dark spot had stopped moving south. It had reversed direction. It was now drifting northward, back toward the higher latitudes, where it had originally formed, back away from the equatorial destruction zone, back into the atmospheric region, where dark spots appear to be most stable. A planetary storm system, moving at the speeds characteristic of Neptune's atmospheric circulation, had changed its own latitudinal trajectory in a way that no fluid dynamics model had predicted, and that no prior dark spot had done within the observational record. Research teams at the University of California, Berkeley, and at NASA's Goddard Space Flight Center, publishing their analysis of the trajectory reversal, noted that it was consistent with a class of behavior seen in large anticyclonic vortices in terrestrial fluid dynamics simulations, a phenomenon where the vortex, as it approaches a region of strong wind shear, interacts with the shear field in a way that generates a restoring force, pushing it back toward higher latitudes rather than allowing the shear to tear it apart. But this behavior had never been observed at Neptune before, and the models were not calibrated well enough to have predicted it. The observation outran the theory. In January of 2021, Hubble returned to Neptune and found something further. A smaller, distinct dark spot had appeared adjacent to the main 2018 dark spot. The companion was approximately 3,900 kilometers across, smaller than the main storm, but still larger than many terrestrial geographic features. Scientists proposed, as their leading hypothesis, that the companion might be a fragment of the main vortex, a piece of the larger anticyclone that had been shed through some disruption process and was temporarily maintaining its own rotational coherence before dissipating. This kind of vortex fragmentation, a large storm system shedding a piece of itself that briefly exists as a separate structure, had never been documented at Neptune before. Like the trajectory reversal, it was behavior that the existing models had not included as a predicted outcome. Both of these findings, the trajectory reversal and the potential fragmentation, point toward the same underlying reality. Neptune's dark spots are not passive objects carried along by the background atmospheric wind field. They are dynamically active participants in a complex system interacting with the wind shear, the jet stream structure, and each other in ways that feed back into their own behavior and alter their trajectories and evolution. The atmosphere is not simply a flow that carries the storms. The storms interact with the flow, modifying it locally and responding to those modifications in ways that are not fully predictable from the existing models. The 2023 observations using the European Southern Observatory's Very Large Telescope added another layer to the dark spot picture that is scientifically important and has not been widely understood in its application. The VLT's Multi-Unit Spectroscopic Explorer, or MUSE, is an instrument that collects a full spectrum at each pixel it observes, meaning that instead of a single image at one wavelength, it produces thousands of simultaneous images at thousands of different wavelengths. Because different wavelengths of light probe different depths in Neptune's atmosphere, shorter wavelengths reflect from higher altitudes. Longer wavelengths penetrate deeper before reflecting. A MUSE observation is effectively a three-dimensional map of the atmosphere at different altitude levels simultaneously. It is the closest thing to a vertical cross-section of Neptune's atmosphere that ground-based instrumentation has ever produced. The MUSE observations of the 2018 dark spot, published in Nature Astronomy in August of 2023 by a team led by Patrick Irwin of the University of Oxford, overturned one of the longest-standing assumptions about what dark spots are. Prior to this work, the dominant model was that dark spots appeared dark because they were clearings in the bright upper-level methane cloud deck holes, where the anticyclonic high pressure had suppressed the cloud formation, exposing the darker atmosphere below. The MUSE data showed this was wrong. Examining the dark spot across its full spectrum, the team found that the darkness was most pronounced at wavelengths shorter than approximately 700 nanometers, and that the spectral pattern was inconsistent with a simple cloud clearing. Instead, the data indicated that the darkness was caused by a real change in the optical properties of the aerosol layer. At depth, the dark spot was dark because something in the atmospheric particles at that altitude was making them less reflective, not because the particles were absent. The team's best explanation: the dark spot likely sits at a pressure level of approximately 5 bar, which corresponds to the altitude in Neptune's atmosphere, where hydrogen sulfide, a chemical compound of hydrogen and sulfur, is cold enough to condense from a gas into ice crystals. At this depth and pressure, the anticyclonic vortex is apparently bringing atmospheric material upward from below, from warmer, deeper levels where hydrogen sulfide exists as a gas into the colder, higher pressure condensation zone where it freezes. The condensing or recently condensed hydrogen sulfide mixed with the existing atmospheric aerosol haze at that altitude creates a chemically modified layer that is darker at visible wavelengths than the surrounding atmosphere. The dark spot is not a hole. It is a window into a chemical process happening deep enough in Neptune's atmosphere that no prior instrument could probe it directly. This finding changes how dark spots need to be understood. They are not surface features of the visible atmosphere. They are driven from below by convective processes operating at pressure levels 5 times higher than the pressure at Earth's surface, at depths where the temperature and chemistry are completely beyond direct observation from any currently operating telescope. The 2023 VLT MUSE result was also the first time a dark spot at Neptune had been observed from the surface of Earth. Every prior observation had been made from spacecraft or from Earth-orbiting telescopes. The adaptive optics system on the Very Large Telescope, which corrects for the blurring caused by Earth's own atmospheric turbulence, was finally sensitive and precise enough to resolve the storm's structure at Neptune's distance of approximately 4.3 billion kilometers from Earth. Michael Wong, a researcher at the University of California, Berkeley, and a co-author of the study, described the result as an astounding increase in humanity's ability to observe the cosmos. At first, he noted, these spots could only be detected by sending a spacecraft to Neptune. Now they can be tracked and studied in 3-dimensional spectral detail from a telescope on Earth. What the MUSE result confirms is that the violence at Neptune is not a cloud-top phenomenon with a simple explanation. The dark spots are the surface expression of deep atmospheric dynamics driven by convective upwelling from altitudes, where the pressure is 5 atmospheres, carrying chemical compounds upward into condensation zones, creating optically modified layers that are detectable from billions of kilometers away, but whose roots extend well below anything we can currently observe directly. The same deep convective processes that generate the dark spots are likely driving the precursor bright companion clouds that appear years before a dark spot becomes visible. Those bright, high-altitude methane ice clouds that showed up in the region where the 2018 dark spot would later form in the years 2015 through 2017, signaling that something was already happening deep in the atmosphere long before the dark spot broke through to the cloud-top levels where Hubble could see it. The storms are not atmospheric surface events. They are the visible consequences of energy moving upward through kilometers of atmospheric depth, originating in processes that are invisible until they break the surface. And all of that energy, the energy driving the supersonic winds, sustaining the continuously cycling dark spots, convecting chemical compounds upward from 5-bar depths, has to be coming from somewhere. Neptune receives approximately 1.5 watts of solar energy per square meter. Earth's strongest tropical cyclones form over ocean surfaces above 26 degrees Celsius, driven by a solar input 900 times larger than what reaches Neptune. Solar energy alone cannot explain a single one of the phenomena documented here. Not the jets, not the vortices, not the deep hydrogen sulfide chemistry cycling through each dark spot. None of it. But there is a second energy source. It is not the Sunday. It is Neptune itself. The second energy source is not a hypothesis. It is a measurement. Neptune radiates into space approximately 2.6 times more energy than it receives from the Sun, a ratio confirmed by instruments aboard Voyager 2 during the 1989 flyby and refined by subsequent observational campaigns. To be precise about what this means, take every photon of sunlight that falls on Neptune in a given period, measure the total energy that represents, and then measure the total infrared energy radiating outward from Neptune across the same period. The outgoing total is larger than the incoming total by a factor of approximately 2.6. The planet is not simply reflecting sunlight and re-emitting it, it is adding energy. The source of that additional energy is Neptune's interior, the deep, hot, high-pressure interior of a world that formed 4.5 billion years ago from the gravitational collapse of solar nebula material, and whose interior has been cooling ever since, and which, despite 4.5 billion years of cooling, is still releasing heat at a rate that makes its atmosphere the most dynamically violent in the solar system. This is the energy inversion that makes Neptune scientifically extraordinary. Planetary science is accustomed to internal heat in giant planets. Jupiter emits approximately 1.67 times the solar energy it receives. Saturn emits approximately 1.78 times. These are significant surpluses, but Jupiter sits 5.2 astronomical units from the Sun and receives about 50 times more solar energy than Neptune does. Saturn sits 9.5 astronomical units away and receives about 17 times more. When you look at internal heat as a fraction of solar input, when you ask how dominant the internal heat source is relative to what the star contributes, Neptune's ratio of approximately 2.6 is not just the largest among the giant planets. It is the most extreme case of internal heat dominance over stellar input in the entire solar system. Neptune's internal furnace is not merely one energy source among two, it is the primary energy source. The Sun, at Neptune's distance, is secondary. The atmosphere of the most distant major planet is driven, first and foremost, by the planet itself. Understanding where this internal heat originates requires going inside Neptune, or rather, going as deep inside Neptune as physics and modeling allow, because no instrument has ever sampled the planet's interior directly. The picture, assembled from density measurements, gravitational data from Voyager 2's trajectory through Neptune's gravitational field, and from laboratory experiments that recreate extreme pressure conditions on Earth, is this. Beneath Neptune's hydrogen-helium-methane gaseous envelope, the interior divides into layers of increasing density and pressure and temperature. The outermost deep layer is dominated by water, not the water of oceans or ice cubes, but water under pressures of hundreds of thousands of atmospheres at temperatures of thousands of degrees. In November of 2024, planetary scientist Burkhard Militzer of the University of California, Berkeley, published models in the journal Proceedings of the National Academy of Sciences, proposing a two-layer structure in which a deep ocean of water exists just below the cloud layers, with a highly compressed fluid of carbon, nitrogen, and hydrogen below that. These two layers, Militzer's models suggest, are compositionally immiscible. They do not mix freely, the way oil and water do not mix, despite occupying the same container. And this layered structure neatly explains not only the unusual heat behavior of both ice giants, but also their unusual magnetic field geometries. Deeper still, at pressures exceeding millions of atmospheres and temperatures exceeding thousands of degrees, an exotic and experimentally confirmed process may be occurring inside Neptune that contributes to its internal energy budget in a way no prior planetary model included. Diamond formation. The interior of Neptune contains carbon delivered during the planet's formation by the same methane and other organic compounds that make up a significant fraction of its bulk composition. At sufficiently extreme pressure and temperature conditions, methane breaks down and carbon atoms are squeezed into the crystalline arrangement that defines diamond. Experiments at the European X-ray Free Electron Laser Facility, published in Nature Astronomy, and further work led by researchers from the SLAC National Accelerator Laboratory and published in Nature Astronomy in January of 2024, have directly confirmed diamond formation in materials representative of ice giant interiors at pressures between approximately 19 and 27 gigapascals conditions, representative of the shallow interior of Neptune, not the deep core, but well below anything that could be called the atmosphere. The 2024 SLAC results also established that this diamond formation occurs at lower pressures and temperatures than previously thought, meaning it happens over a larger volume of Neptune's interior than earlier models predicted. The consequence of diamond formation for Neptune's interior heat budget is indirect but real. Once formed, diamonds are denser than the surrounding icy material. Dense objects in a gravitational field sink. The diamonds sink slowly over geological time, releasing gravitational potential energy as they fall, heating the material they pass through. The SLAC researchers describe this as diamond rain, a slow gravitational precipitation of crystalline carbon through thousands of kilometers of interior material. The diamond rain generates heat. It also stirs the surrounding layers of conductive ice, including the layers of superionic water that theory predicts exist at the depths where temperature and pressure are sufficient to break water molecules into oxygen crystal lattices with mobile hydrogen ions. And that stirring contributes to the convective motions within the conductive interior that drive Neptune's magnetic field. Diamond rain is not just an exotic interior curiosity. It is, as far as current models suggest, one of the mechanisms by which Neptune's interior maintains its heat production and transfers that heat upward toward the atmosphere. At the deepest accessible region, the superionic water predicted by theory represents another layer of the interior heat story. Superionic water is a phase of matter in which oxygen atoms arrange themselves into a crystalline lattice, the way atoms arrange in solid ice, while the hydrogen ions, stripped from the water molecules, move freely through that lattice as a conducting fluid. Superionic water is simultaneously solid-like in its oxygen framework and liquid-like in its hydrogen conductivity. It was predicted theoretically and then confirmed experimentally in recent years. It conducts electricity. It generates magnetic fields when the planet's rotation drives large-scale convection through it. And its presence in Neptune's interior, combined with the way the conductive layers are geometrically arranged relative to the planet's rotation, is the leading explanation for one of Neptune's other remarkable properties: its dramatically tilted and off-center magnetic field. Neptune's magnetic field is unlike that of any other giant planet in the solar system. Earth, Jupiter, and Saturn all have magnetic fields that are approximately aligned with their rotation axes. The field axis and the spin axis are within 12 degrees of each other at Earth, within 10 degrees at Jupiter, within less than 1 degree at Saturn. Neptune's magnetic axis is tilted approximately 47 degrees from its rotation axis. The field is also dramatically offset from the planet's physical center by approximately 55% of Neptune's radius. This means the center of Neptune's magnetic dipole is not anywhere near the center of the planet. It is displaced toward one hemisphere, sitting in a portion of the interior that is closer to the cloud tops than to the planetary core. As Neptune rotates, completing a full rotation in approximately 16 hours and 6 minutes, this tilted, offset magnetic field sweeps through space, exposing different parts of the planet to different field orientations at different times. The magnetosphere, the bubble of space carved out by Neptune's magnetic influence against the solar wind, shifts and warps with each rotation, creating a dynamic interaction between the solar wind and the planet's environment that is more complex than at any other giant planet. The implication of the magnetic field's geometry for where the field is generated points directly to the interior structure. The dynamo generating Neptune's field must be operating in the outer conductive layers of the interior rather than deep near the core, because only a dynamo source in the outer layers could produce a dipole so severely displaced from the planet's center. This is consistent with the superionic water model. If superionic water exists in Neptune's interior at the right depth and with the right convective properties, it could generate a magnetic field with exactly the tilted, offset geometry that Voyager 2 measured. The magnetic field is, in this interpretation, both a consequence of the interior heat driving convection and a pointer toward where in the interior that heat is concentrated. All of this interior physics, the diamond rain, the superionic water, the layered immiscible structure, the off-center dynamo, is important, not as a catalogue of exotic interior phenomena, but as the physical mechanism by which Neptune's internal heat is generated and sustained. The primordial heat from formation, the gravitational energy released when solar nebula material collapsed together to make a planet, is the ultimate origin of Neptune's internal heat, as it is for all giant planets. The question is why Neptune's interior is still releasing that heat at a rate that exceeds the solar input by a factor of 2.6 when its structural twin Uranus has lost its primordial heat to the point where it emits essentially zero surplus. The diamond rain, the phase transitions within the interior, the compositional layering that either allows or blocks efficient heat transport toward the surface. These are the mechanisms that determine how fast a planet loses its formation heat, and they appear to operate differently in Neptune than in Uranus, despite the two planets' broad structural similarity. The Uranus-Neptune comparison is the most powerful tool available for isolating what makes Neptune violent. Uranus emits approximately 1.1 times the energy it receives from the Sun, a ratio so close to 1 that within measurement uncertainties, Uranus is in thermal equilibrium with its star. The excess, if real, is negligible. Uranus's interior has, for all practical purposes, gone dark as far as the atmosphere is concerned, and the atmospheric consequence is precisely what the gradient intuition predicted for cold outer giants, a quiet planet, largely featureless in most observations, without the persistent large-scale vortex systems, without the supersonic retrograde jet, without the cycling storm generation that has made Neptune one of the most dynamically documented worlds in the outer solar system. A paper published in June of 2025 in the Astrophysical Journal examined different inhomogeneous evolutionary histories for Uranus and Neptune using modern models of interior composition and convective behavior. The paper proposed that the observed luminosity difference between the two planets could be explained by a difference in whether their outer envelopes were initially well mixed or compositionally stratified. In Neptune's model, if the initial entropy of the forming planet was high enough to allow convective mixing across the outer 40% of its envelope, that mixing would have established an efficient heat transport pathway from the interior to the atmosphere that has been running continuously for 4.5 billion years. In Uranus's model, if the outer envelope was initially stratified in a way that inhibited that convective mixing, heat transport from the interior to the atmosphere would have been suppressed, and the observable luminosity, the internal heat flux, would have been negligible from the beginning. The difference between a world like Neptune and a world like Uranus may, in this framework, trace back to a difference in the initial conditions of planetary formation, subtle variations in how material accreted and how much entropy the forming body acquired that set the two planets on divergent evolutionary paths from the start. This is a hypothesis, not a confirmed model. Other research groups propose different explanations. The impact hypothesis that a large collision early in Uranus's history disrupted convection in a way that sequestered heat in the interior rather than allowing it to reach the surface remains a viable candidate, especially given Uranus's 98-degree axial tilt, which is itself strong evidence of a massive historical impact. The convective inhibition hypothesis, that condensation of methane and water in Uranus's atmosphere creates stable layers that suppress the convective plumes that would otherwise carry internal heat to the surface, has been examined quantitatively in peer-reviewed work and found to be significant but insufficient alone to explain the full magnitude of the Uranus-Neptune difference. The compositional layering hypothesis that immiscible layers in Uranus's interior block heat from reaching the outer regions is consistent with the two-layer models Militzer published in 2024. No single explanation has achieved consensus. What has achieved consensus is the observation that drives all these explanations. Neptune's interior is releasing heat at a rate that makes it the most dynamically active giant planet atmosphere in the solar system. And Uranus, its structural twin, is not. That contrast is what the science of ice giant planets has been trying to explain for more than 3 decades. Since Voyager 2 completed its tour of both planets in the late 1980s, it is still trying. The internal heat problem is described in the planetary science literature as an outstanding major problem, not a solved one. To fully appreciate the scale of the contrast, it helps to be precise about what the Uranus and Neptune measurements actually represent. When Voyager 2 flew past Uranus in January of 1986, it measured the planet's effective temperature, the temperature at which Uranus radiates as a thermal emitter, and found it at approximately 59.1 Kelvin, the expected equilibrium temperature. The temperature Uranus should have from solar heating alone at its distance from the Sun is approximately 58 Kelvin. The measured temperature and the predicted equilibrium temperature are indistinguishable within measurement uncertainty. Uranus is, to a precision of better than a few %, exactly as warm as solar heating alone should make it. The interior contributes nothing detectable to the energy output. Compare this to Neptune. Its effective temperature is approximately 59.3 Kelvin, and its equilibrium temperature from solar heating at its greater distance should be approximately 46.6 Kelvin. Neptune is 13 Kelvin, warmer than the Sun alone can account for. 13 degrees may sound modest against the backdrop of a temperature measured in Kelvin, starting from absolute zero. But the energy flux required to maintain that difference, radiating 2.6 times the solar input continuously, is substantial, and it has been sustained for 4.5 billion years. The energy accounting gets even more revealing when you factor in the relationship between the 2 planets and Jupiter, and when you consider the absolute numbers rather than just the ratios. Jupiter's internal heat surplus is approximately 1.67 times its solar input, and Jupiter is receiving far more solar energy than Neptune. In absolute terms, watts of internal heat radiated per square meter of planetary surface, Jupiter's internal heat output per unit area is roughly similar to Neptune's. The difference is that Jupiter is enormous. Its radius is approximately 2.8 times Neptune's, making its total surface area approximately 8 times larger. So its total internal heat output is substantially larger in absolute terms. But the ratio of internal heat to solar input, the number that tells you how important the internal heat is relative to the Sun for driving the atmosphere, is far larger at Neptune than at Jupiter. Neptune's atmosphere operates in a regime where internal heat is not a supplement to solar driving. It is the primary driver. The Sun is the supplement. This inversion is unique in the solar system, and it is what makes Neptune meteorologically unlike anything else in the planetary family. The question of why Uranus has allowed its internal heat to dissipate, or, alternatively, why Uranus has sequestered its heat in a way that prevents it from reaching the atmosphere, is not resolved, and the honest account of Neptune's violence cannot avoid sitting with that unresolved status. The most recent peer-reviewed models propose that the 2 planets may have had different initial entropies at formation, different amounts of thermal energy locked into the bulk of the planet at the moment it finished accreting, and that this initial difference set them on divergent evolutionary paths before any subsequent difference in atmospheric structure or impactor history could be invoked. Under this scenario, Neptune simply formed hotter, with more internal energy available to radiate, and has been radiating it efficiently ever since. Uranus formed cooler, or sequestered its available heat more efficiently early in its history, and has been near equilibrium with the Sun for most of its existence. Whether this is the correct explanation, or whether one of the impact disruption, compositional stratification, or convective inhibition hypotheses better describes the divergence, the empirical comparison between the two planets remains the cleanest natural experiment available. Uranus and Neptune are as similar as two planets in the solar system can be, while being distinct objects. Their bulk properties match at a level that no other pair of major planets does. The atmospheric behavior difference between them, violent versus quiet, internally driven versus solar driven, cycling storm systems versus near featurelessness, is entirely accounted for by the internal heat difference. There is no other significant variable that differs between them in the right direction and to the right degree to explain the atmospheric contrast. The internal heat is the answer. The reason the internal heat differs between them remains the outstanding question. And while that question is unresolved, the story of Neptune's violence is complete in its essentials. The planet has the heat drives the atmosphere, and no model built from distance and temperature and solar energy alone would have predicted either the heat or the violence. There is one further dimension of Neptune's internal heat story that belongs in this part of the account, and it connects the deep interior physics to the surface atmosphere in a way that is more direct than convection models usually suggest. Neptune's rotation period of approximately 16 hours and 6 minutes means that the planet completes a full rotation in less than 2/3 of an Earth day. For a planet with Neptune's physical dimensions, approximately 49,500 kilometers in diameter, that rotation rate corresponds to significant velocity differences between the equatorial and polar regions as the planet spins. The Coriolis effect, which is the deflection of moving objects in a rotating frame, is proportional to the rotation rate. At Neptune's rotation rate, the Coriolis effect on atmospheric gas moving horizontally, as in the retrograde equatorial jet or the prograde mid-latitude jets, is substantial. It is the Coriolis effect that organizes the atmospheric circulation into discrete jet streams, rather than allowing it to flow freely in all directions. The internal heat provides the energy. The rotation provides the organizing structure that concentrates that energy into the coherent, high-velocity jet streams that produce the wind records. A planet with the same internal heat but slower rotation would distribute that energy differently and might produce a more turbulent, less structured atmosphere without the clear jet stream organization that makes Neptune's wind speeds so extreme. Neptune's 16-hour rotation is part of the machinery that converts internal heat energy into the fastest winds in the solar system. Since Voyager 2 completed its tour of both planets in the late 1980s, it is still trying. The internal heat problem is described in the planetary science literature as an outstanding major problem, not a solved one. What that acknowledgement means for the story of Neptune's violence is not a weakening of the conclusion the violence is observed and measured and documented, but a deepening of the mystery at its root. The most violent major planet in the solar system is powered by a mechanism that planetary science cannot yet fully characterize. The furnace is real, its precise fuel source, and the reasons its twin planet lacks an equivalent furnace remain imperfectly understood. The connection between Neptune's rotation rate and its internal heat also carries implications for what the atmospheric circulation looks like below the cloud tops in the region of the atmosphere that we cannot directly observe, but that fluid dynamics models are beginning to characterize. the outermost 0.2% of Neptune's mass. The shell, approximately 1,100 kilometers deep, where the cloud-top winds are measured, is where the fastest jets exist. But that thin shell sits above a vast interior, and the transition from the high-velocity surface jets to the slower interior rotation must occur somewhere in the middle atmosphere. Exactly where that transition happens, and what the wind structure looks like at intermediate depths between the cloud tops and the deep interior, is something that no current instrument can measure directly. Models suggest that the winds decelerate sharply below the cloud top level, converging toward the rotation rate of the deep interior. The gravitational data from Voyager 2's flyby, which provided the only direct constraint on the depth of the wind system, is consistent with this picture. The winds are genuinely shallow, confined to the thin outer atmospheric shell, and they represent a surface expression of deep interior dynamics rather than a deep atmospheric circulation in the style of Jupiter's broad belt zone structure. The fact that the most violent winds in the solar system are concentrated in such a shallow layer, powered by internal heat rising from thousands of kilometers below, is one more reminder that Neptune's violence does not come from where intuition would place it. Saturn's atmosphere, by comparison, shows a different depth structure. Its jet streams appear to penetrate significantly deeper into the planet, driven by a combination of internal heat and the solar energy input that Saturn, being closer to the Sun, receives more abundantly. Jupiter's jet streams penetrate to depths of thousands of kilometers, anchored in the deep interior dynamics. Neptune's jets are shallow, but faster than either. The energy concentration at the very surface of Neptune's atmosphere, the result of internal heat that cannot penetrate the surface jet stream layer efficiently. Instead, depositing its energy into the thin outer shell is the physical mechanism that converts a general internal heat surplus into the specific, record-breaking wind velocities that define Neptune's atmospheric violence. The furnace is deep, the expression of the furnace is at the surface, and the surface, thin as it is in mass terms, moves faster than anywhere else in the solar system's atmosphere. And now, in 2025, a new instrument is beginning to illuminate not just the interior's heat output, but the consequences of that heat operating at every altitude in Neptune's atmosphere simultaneously, from the deep 5-bar layers where dark spot chemistry originates, upward through the cloud decks, through the stratosphere, all the way to the ionosphere, where the James Webb Space Telescope found something that changed what scientists thought they knew about the upper boundary of Neptune's violence. What JWST found at the top of Neptune's atmosphere is the final layer of the story, and it is the layer that makes clear why everything we thought we knew about this world has been a series of successive approximations, each revised by a better instrument, each revealing that Neptune is more active, more dynamic, more changeable than the one before suggested. The furnace drives the atmosphere from the bottom. What JWST found shows that the atmosphere is also being transformed from the top, and the rate of transformation, there is something no model, calibrated to any prior measurement, had predicted. The James Webb Space Telescope turned its mirrors toward Neptune in June of 2023. The instrument it used was its near-infrared spectrograph, a device capable of separating incoming infrared light into its component wavelengths with a precision that far exceeds what any prior observatory, ground-based or space-based, could achieve for an object at Neptune's distance. What the spectrograph was searching for was something that had been predicted to exist at Neptune for more than 30 years and had repeatedly evaded detection: the trihydrogen cation, designated in chemistry as H3+, a molecular ion consisting of 3 hydrogen atoms sharing 2 electrons and carrying a net positive charge. H3+ forms in planetary ionospheres when energetic processes, particularly auroral activity, where charged particles from the solar wind slam into the upper atmosphere along magnetic field lines, deliver enough energy to ionize and restructure the ambient hydrogen gas. The ion had been found and studied at Jupiter, Saturn, and Uranus for decades. Models consistently predicted it should be present at Neptune. Every instrument that searched for it at Neptune found nothing. The 2023 JWST data found it immediately. Not faintly, not at the edge of detectability. Henrik Mellin of Northumbria University, who led the research team analyzing the data and published the results in Nature Astronomy in March of 2025, described his reaction when the emission line appeared in the spectrum as stunned. The H3+ detection at Neptune was, in the spectrograph's data, not subtle. It was a prominent emission signature, the kind that, in retrospect, should have been clearly detectable with earlier instruments, if those earlier instruments had been looking at an atmosphere at the temperature Voyager 2 measured in 1989. The reason the previous instruments found nothing was not that H3+ was absent. It was that Neptune's upper atmosphere had become cold enough over the intervening 34 years to suppress the emission to levels that those instruments could not distinguish from background. When JWST measured the temperature of Neptune's ionosphere, the upper atmospheric region where the aurora forms, where H3+ exists, where solar wind energy is deposited through the magnetic field, the result was a number approximately half of what Voyager 2 had recorded in 1989. Not a few percent cooler, not a modest seasonal fluctuation, half. The average upper atmospheric temperature in 2023 was a factor of 2 lower than what Voyager measured 34 years earlier. Mellin described this finding in the published paper with a precise and striking formulation. The energy balance of Neptune's upper atmosphere is regulated by physical processes acting on a timescale shorter than both Neptunian seasons, which last approximately 40 Earth years, and the solar cycle, which lasts approximately 11 years. Whatever is causing the upper atmosphere to change temperature by a factor of 2 over 3.5 decades is not the slow seasonal cycle of a planet orbiting once every 165 years, and it is not the 11-year oscillation of solar activity. It is something faster than either of those, something operating at Neptune's upper atmosphere on its own independent timescale. This finding is remarkable in what it reveals about the depth of Neptune's dynamism. The violence documented at the cloud tops, the supersonic winds, the cycling dark spots, the hydrogen sulfide chemistry at 5 bar pressure exists because internal heat drives convection upward from the deep interior. But the upper atmosphere, the ionosphere 1,000 kilometers above the cloud tops, is changing independently on its own timescale, driven by processes that are not simply the top end of the same convection that produces the winds below. Neptune's atmosphere is not a uniform system with one driving mechanism. It is a complex, multiply-driven system in which different altitude regimes operate on different timescales, respond to different energy sources, and change in ways that are not predictable from measurements made at other altitudes or at other times. Before examining that geometry, It is worth sitting for a moment in what Mellin's published conclusion actually says about the timescale of the change, because it points to something important about the category of event we are dealing with. The Nature Astronomy paper states explicitly that the energy balance of Neptune's upper atmosphere is regulated by physical processes acting on timescales shorter than Neptunian seasons and shorter than the solar cycle. A Neptunian season lasts approximately 40 Earth years, because Neptune's year is 165 Earth years, and it has 4 roughly equal seasons. The solar cycle lasts approximately 11 years. If the upper atmospheric temperature can change by a factor of 2 in 34 years, a period that is less than 1 Neptunian season and roughly 3 solar cycles, then the energy balance is responding to something that operates faster than either of those well-characterized periodic forcings. The implication is that Neptune's upper atmosphere is not in a slowly varying quasi-equilibrium. It is in a state of active, rapid adjustment, responding to inputs that we have not yet characterized well enough to predict. This is a world whose upper atmosphere changes by a factor of 2 in temperature over a human lifetime, without anyone noticing, because no instrument was watching closely enough. The practical consequence of the temperature drop for auroral visibility is precise and informative. The intensity of H3+ emission scales very steeply with temperature. The warmer the ionosphere, the brighter the emission, and the relationship is not linear, but exponential in character. A factor of 2 reduction in temperature corresponds to a reduction in H3+ emission intensity by roughly 1 to 2 orders of magnitude, depending on the specific conditions. This means that if Voyager 2's 1989 temperature measurement had remained accurate, the auroras would have been detectable with ground-based telescopes in the 1990s. The fact that they were not detected was interpreted as an anomaly in Neptune's ionosphere, as evidence that H3+ was simply not present, or present only at very low levels, for reasons that existing models could not explain. Dozens of observing campaigns searched for H3+ at Neptune between 1989 and 2023 and found nothing. That absence was used to argue that Neptune's ionosphere was uniquely different from those of the other giant planets in ways that were not well understood. JWST's measurement clarified the situation. The ion was there all along. The ionosphere was changing underneath the predictions. And the predictions were wrong because the baseline they were built on was no longer accurate. The geometry of Neptune's auroras, revealed for the first time in the JWST data, adds another dimension of strangeness that is worth dwelling on. On Earth, auroras form near the geographic poles because Earth's magnetic field is approximately aligned with its rotation axis, and the field lines that channel incoming solar wind particles to the atmosphere converge near the poles. The northern lights appear in the northern polar region for exactly this reason. At Jupiter and Saturn, whose magnetic fields are also approximately aligned with their rotation axes, the same pattern holds. Auroral activity is polar. At Neptune, whose magnetic field axis is tilted 47 degrees from the rotation axis, and whose field center is displaced 55% of the planet's radius from the planet's physical center, the geometry is completely different. The magnetic poles, the points where the field lines converge and channel energetic particles most efficiently toward the atmosphere, do not sit near Neptune's geographic poles. They sit near the mid-latitudes, at positions that, on Earth, would correspond roughly to the latitude of South America or Australia. As Neptune rotates through its 16-hour day, these mid-latitude magnetic poles sweep around the planet, exposing different longitudes to auroral energy deposition at different times, creating a dynamic auroral pattern that covers a broad band of mid-latitude atmosphere rather than the tight polar ovals seen at Jupiter and Saturn. The JWST images show Neptune's infrared auroras as splotches of emission clustered near the southern mid-latitudes, consistent with this off-center, tilted magnetic field geometry. Leigh Fletcher of the University of Leicester, a co-author on the Mellin 2025 paper, described JWST's detection as having finally opened the window onto the last previously hidden ionosphere of the giant planets. For 34 years, Neptune was the only giant planet in the solar system whose upper atmosphere could not be directly probed through H3+ emission. JWST closed that gap, and in doing so, revealed that the gap had been maintained all along, not by the absence of auroral activity, but by a factor of 2 temperature change that no prior instrument had the sensitivity to detect, while also being able to characterize the ionospheric emission. What does a factor of 2 upper atmospheric cooling mean for Neptune's overall behavior? The published Nature Astronomy paper includes a specific and carefully worded conclusion. The cooling shows that Neptune's ionospheric energy balance is regulated by processes operating on a time scale shorter than the solar cycle. This means Neptune's upper atmosphere is responsive. It is not a static equilibrium maintained by the slow balance of solar input against radiative output. It is actively changing, and it is changing in response to processes that act faster than the Sun's 11-year magnetic cycle. One candidate is the interaction between the solar wind and Neptune's unusually structured magnetosphere. As the solar wind varies in density and speed, and magnetic field orientation variations that occur on timescales of days to years, it deposits energy into Neptune's ionosphere in patterns that are amplified and complicated by the tilted, off-center magnetic field. A slight change in solar wind conditions produces a larger and more geometrically complex response at Neptune than at other giant planets, precisely because the magnetic field geometry is so unusual. The ionosphere heats or cools in response on timescales that can be much shorter than a solar cycle if the coupling between the solar wind and the ionosphere is efficient. The stratospheric cooling documented by Michael Roman and colleagues in a 2022 paper published in Planetary Science Journal adds the middle layer to this picture. That study, examining 20 years of infrared photometry of Neptune's stratosphere, found that the southern hemisphere's stratospheric temperature had dropped by approximately 8 degrees Celsius between approximately 2000 and 2022, a cooling that occurred despite the southern hemisphere being in its summer season, when solar heating should, if anything, be producing slight warming. The leading explanation for the stratospheric cooling was the same storm-driven mechanism identified in Part 2, deep atmospheric convective events reshaping the cloud structure, altering how much ultraviolet radiation penetrates to different altitude levels, and modifying the photochemical heating rates that control stratospheric temperature. The storms of the cloud tops are not isolated events. They are connected through atmospheric coupling to the layers above them. The violence at the cloud tops propagates its consequences upward into the stratosphere. The stratospheric changes then propagate upward still further into the mesosphere and ionosphere, where they interact with the solar wind coupling effects on additional timescales. Neptune's atmosphere is a layered, coupled system in which violence at any one level propagates consequences to every other level, and the timescales of those consequences span from hours for individual storm events to decades for the upper atmospheric temperature changes that JWST has now documented. This is the genuinely new conceptual angle that Part 4 can contribute to the complete story of Neptune's violence. Neptune's atmosphere is not just violent, it is violently coupled across altitude. The internal heat drives the deep convection. The deep convection generates the dark spots and the supersonic winds. Those features modify the cloud structure and the penetration of solar ultraviolet radiation into the stratosphere, cooling it on decadal timescales. The stratosphere communicates with the ionosphere. The ionosphere, responding to the solar wind through a magnetic field geometry that is uniquely complex among giant planets, cools by a factor of 2 in 34 years through processes that operate faster than the solar cycle. And that cooling at the ionosphere suppresses auroral emission enough to hide it from every instrument built before JWST. The violence does not stay at one altitude. It fills the atmosphere from bottom to top, coupling each layer to the ones above and below, producing changes that span from the fastest atmospheric timescales to timescales longer than any human observational campaign has yet covered. Now, stand back from that picture and consider what it means for how well we understand Neptune. The JWST data confirmed something that 22 years of prior ionospheric prediction had gotten wrong, not because the physics was wrong, but because the baseline temperature measurement from 1989 was already outdated by the time researchers were using it to make predictions in the 1990s and beyond. Neptune's upper atmosphere had already begun its factor of 2 cooling at some point after Voyager's visit, and that cooling was happening invisibly, undetected, while the entire post-Voyager program of Neptune prediction was being built on a temperature that was no longer accurate. Every model of Neptune's expected auroral intensity built between 1989 and 2023 was calibrated to a baseline that the planet had already moved away from. The planet changed. The models, unable to measure the change, did not. This is Neptune's defining characteristic as a subject of scientific study. It changes faster than the instruments studying it can track, and it changes in ways that the prior state of the instruments would not have detected, even in principle. The Voyager flyby was the first close look, and it produced the wind record and the Great Dark Spot. Hubble's monitoring found the Great Dark Spot gone and replaced in 5 years, then documented 4 more dark spot cycles, then found the 2018 dark spot reversing direction and shedding a companion. The VLT with Muse found that dark spots are deep chemical events, not cloud clearings. JWST found that the upper atmosphere had cooled by half without anyone knowing. Each instrument, at the limit of its capability, found something that required a revision of the picture assembled from all prior instruments. The planet refuses to be fully characterized by any single generation of observational technology. Every generation of technology finds something the last one missed. What this implies, carried forward to the future, is both scientifically specific and genuinely humbling. The only spacecraft ever to visit Neptune is Voyager 2, which flew past in 1989 and has been traveling outward into interstellar space ever since. Neptune has no orbiting mission. It has no atmospheric probe. It has no lander on Triton. The entire body of knowledge, assembled since 1989, has come from remote observation across 4 to 5 billion kilometers of space, using instruments whose primary limiting factor has consistently been not the scientific questions, but the available photons, the faint light that reaches Earth from a world lit by a sun whose intensity, at that distance, has been reduced to 1/900th of what Earth receives. And still, with those faint photons, each new instrument has found something the last one missed, something that changed the story. A dedicated Neptune orbiter, a spacecraft that would spend years in stable orbit rather than days in flyby transit, remains the scientific priority identified in NASA's most recent planetary science decadal survey. Given current funding timescales and development schedules, such a mission would not launch before the late 2030s at the earliest and would not reach Neptune until the 2050s. Between now and then, everything we learn about the most violent major planet in the solar system will come from telescopes pointed across several billion kilometers of space. JWST has its own orbital constraints. The geometry of its position at the second Lagrange point limits how frequently and for how long it can observe Neptune. The observing windows are narrow. The data that comes through those windows is, for all its infrared sensitivity, still a spectrum of a disk a few arc-seconds across from a planet 5 billion kilometers away. The spatial resolution is not the resolution of an orbiting spacecraft looking down at cloud structures from a few thousand kilometers altitude. It is the resolution of a photon budget, refined by the best engineering in human astronomical history, stretching across a gulf that no human-built object except Voyager 2 has ever crossed. And yet, what those remote measurements have shown, what Voyager 2 found in 1989 and Hubble has built upon across 3 decades, and VLT-MUSE refined in 2023, and JWST revealed in 2020, 25 is a picture of extraordinary violence sustained by extraordinary internal heat, operating at every altitude simultaneously, changing on timescales shorter than the planet's own seasons, producing phenomena at the ionosphere that were hidden from every prior instrument by a temperature change none of those instruments could detect. The most violent major planet in the solar system has been doing all of this at the far edge of the planetary system across the entire history of human civilization, and for the first time in that history, human instruments are becoming sensitive enough to begin to see the full depth of what it has been doing. The comfortable picture of the outer solar system, the gradient, the assumption of quiet at the edge, the intuitive mapping of cold and distant onto still and dormant, was not a foolish picture. It was built from the best available information, reasoning in the most natural direction. It was also completely wrong about the farthest major planet, and the degree to which it was wrong has become clearer with each passing decade of observation. Neptune does not represent the end of the solar system's activity. It represents the proof that the solar system's activity is not organized the way human intuition suggests. The energy source that matters for Neptune's atmosphere is not the Sunday, it is Neptune. And Neptune has enough of its own heat, sustained by deep interior processes that we are still learning to characterize, to produce the fastest winds, the most dynamically complex storms, and the most surprising upper atmospheric changes in the entire planetary system. The blue is a color produced by methane-absorbing red light. The serene appearance is the visual impression of a cold, dim, distant world lit by a faint star. Both of those things are real, and behind them, inside them, expressed through them, in the form of supersonic, equatorial jets and hydrogen sulfide condensation, vortices and factor of 2 ionospheric cooling and diamond rain sinking through superionic water is the most violent. atmospheric system orbiting our Sun. That is what is happening at the edge of the planetary family. It has been happening since long before we developed the instruments to see it. And the picture we have assembled across 36 years of post-flyby observation is still, by the measure of what a dedicated orbiting mission would reveal, only a beginning. The gradient was wrong. The cold is real. Consider what the full 36-year observational record, the stratospheric cooling documented by Roman and the ionospheric cooling documented by Malin, are not two separate phenomena pointing towards separate explanations. They are two altitude levels of the same coupled atmospheric system responding to the same underlying driver, a planet that is never stable, that is constantly adjusting its thermal structure from the deepest detectable atmospheric levels to the highest. The Roman 2022 stratospheric result and the Mellin 2025 ionospheric result, taken together, describe an atmosphere in which the consequences of internal heat propagate all the way from the 5-bar depths, where dark spot chemistry originates, to the ionosphere at the top of the observable atmosphere, and in which those consequences change over decades in ways that none of the instruments studying the planet had the sensitivity to track in real time. JWST is the first instrument that is, in principle, capable of tracking ionospheric temperature changes at Neptune with the necessary precision over time. The observing campaign designed around Neptune monitoring across a full solar cycle will, within the next decade, either confirm the solar wind coupling hypothesis for the upper atmospheric cooling or point towards something else, something currently outside the available models. As the cause, either result will be informative. Neptune has a reliable history of providing informative surprises when a better instrument looks. The picture of Neptune in 2025 is therefore a picture defined as much by what is unknown as by what is known. The atmospheric violence is documented and measured. The internal heat is confirmed and quantified. The dark spot cycle is observed across 3.5 decades. The ionospheric cooling is confirmed by JWST. The deep interior physics superionic water, diamond rain, immiscible layering is supported by laboratory experiments and theoretical models, but not directly observed. The reason Uranus has no equivalent internal heat surplus remains an unresolved major problem in planetary science. The timescale and mechanism of the ionospheric cooling remain uncharacterized. The full extent of the coupling between deep atmospheric convection, stratospheric temperature, and ionospheric energy balance remains incompletely mapped. Neptune is, as a scientific subject, a world whose violence is clear and whose mechanisms are still being assembled. The violence is the confirmed observation. The explanation of that violence at its deepest level is the active research problem of Neptune. From Voyager 2's flyby to JWST's auroral detection actually represents as a dataset. In those 36 years, every major category of new observation has produced a result that prior models did not predict. Voyager 2 found supersonic winds and Earth-sized storms where models predicted atmospheric quiet. Hubble found those storms gone in 5 years and replaced by new ones. The 2018 dark spot reversed direction. VLT Muse found dark spots are deep chemical events rooted at 5-bar pressure, not cloud clearings. JWST found the ionosphere had cooled by half. The pattern is not random. It is systematic. Each time, a more capable instrument was applied to Neptune. The instrument found behavior that required a revision of the model. This is not how planets typically behave under scientific observation. Most planetary targets, as instruments improve, yield refinements of existing models, better precision on measurements that confirm what was expected, with occasional anomalies that can be explained within the existing framework. Neptune, by contrast, has produced a structural revision of its dominant model at every observational advance. The previous model was not approximately right, and the new instrument refined it. The previous model was wrong about something fundamental, and the new instrument revealed the wrongness. This is what makes Neptune scientifically distinctive, beyond its atmospheric violence. Its violence is extreme, but extreme is a quantitative distinction. What is qualitatively distinctive is that Neptune continues to hide things from us, and the things it hides are not details. They are the defining features of the planet's behavior. The temperature of the ionosphere, wrong by a factor of 2 for 3 decades. The nature of dark spots, wrong about the mechanism for 34 years. The reversal behavior of storm trajectories, not predicted by any prior model. These are not edge cases, they are the central phenomena. And every one of them was only revealed when an instrument capable of the necessary measurement was finally pointed at the planet. And it does not mean quiet. The distance is real, and it does not mean dormant. The beauty is real, and it is not a promise of peace. Neptune is what the evidence shows it to be. A world that violates the intuition, sustains itself from within, changes faster than models predict, and hides its most dramatic changes from every instrument until a better one arrives, the last planet, the most violent one, still telling us things we did not know, and still holding more of them in reserve.